So last lesson we learned about perfect induction and Venn diagrams. Those are sort of secondary tools, if I'm being totally honest. The primary tool for proving the equivalency of two statements is Boolean algebra. Now, Boolean algebra, named after George Boole, the person who really sort of formalized it, this is the foundation of the math that underlies binary arithmetic and digital circuits. So we refer to it as Boolean algebra, and then binary arithmetic or mathematics, and then we have digital circuits. So we're really going to be spending most of our time talking about digital circuits, but Boolean algebra is a powerful tool to help us to simplify and analyze those circuits. Now, Boolean algebra has a lot of properties and theorems, just as regular algebra does. And so here you can see some of these are over here. So you can see the commutative property. Commutative just refers to the fact that you can flip the two inputs on either an OR operation or an AND operation. Remember, we don't think of this as plus or multiplication or addition and multiplication. We could think of this as OR and AND. The associative property says that you can adjust the grouping symbols. So I can have X or the quantity y or z, and that's exactly the same thing as the quantity x or y or z. And I can do the same thing with the AND operation as well. By the way, this is the first time that I'm showing you that when you're doing the AND operation, we can omit that dot in the middle. Sometimes it's included if you want to be really formal. Other times it's not included, especially if you're doing a lot of algebra. But just as in regular algebra, we omit the dot sometimes. And actually, most of the time, I omit the dot. And the same thing is true when you're doing an AND operation. So if you see something like this, and there's just two variables next to each other, just know that that just means that those variables are ANDed together. The distributive property is very powerful. This says that if you have x and, notice that there's sort of a missing and operator there, x and the quantity y or z, well, this can distribute the x into both of those terms. It becomes x and y or x and z. And that's exactly what you would expect if this were a regular algebraic expression. And then we can more generally do a FOIL, the first, outer, inner, last. And so you can see that if we have x or y and the quantity x or y and the quantity w or z, we end up with four terms, which is each of those four possible combinations. So the distributive property allows us to take a complicated but compact expression and make it into a longer expression that has simpler terms. Now, there are other algebraic theorems, and these all have special names. There's the identity theorem with 0. There's the identity theorem with 1. There's the self-identity theorem, I think it's called. But if you think about each of these, they make sense. No matter what you AND with 0, you're always going to get 0. And no matter if you have anything ANDed with 1, you're just going to get the original thing back again. ANDing it with 1 doesn't make any difference. If you AND something with itself, you're going to get that same thing back again. Here's a very interesting one. X ANDed with not x. This is like saying, I want you to show me something that is a chair and also not a chair at the same time. There is no such thing as something that is a chair and not a chair. There is no such thing as something that is both x and not x at the same time. So if you ever see both x and what we call its complement, its opposite, in the same term, that's going to go to 0 right away. If you have x or 0, the or 0 doesn't make any difference. You're just going to get x back again. X or 1, well, no matter what you OR with 1, you're just going to get 1 out. X or x, doesn't matter if you OR something with itself, you get that same thing back again. And then x or not x. So if you take everything that is in x, and then you also take everything that is not in x, you get everything. And so x or not x is just equal to 1. And then down here you can see x or x and y. Well, that's also, we can prove that that's just equal to x. And then one of the ones that we're going to do in an example is x or y and x or z. That's just equal to x or y and z. And then the one that we just proved by perfect induction and the Venn diagram, x or not x and y is equal to x or y. So these are some algebraic theorems that can come in very handy when you're trying to prove something using Boolean algebra. There's also one other pair of equations known as DeMorgan's Theorem. DeMorgan's Theorem is very important, and it probably seems confusing when you see it at first glance, but I promise you that there will be problems that DeMorgan's Theorem can solve that no other tool can solve. What DeMorgan's Theorem allows you to do is it allows you to break a large overbar. And remember that this overbar represents an inverter or a knot. It allows you to break that large inverter into two smaller inverters. So I've broken it. It used to be across the entire term, and now it's separate inverters across the two individual terms. But notice that when I did that, I had to convert the OR to an AND. I have to change the nature of the operator. And the same thing is true here. If I have a large overbar with an and, I can break it into a small overbar, and an or. So this means that you can break the large overbar into two shorter overbars, but you have to flip the nature of the operator. Sort of a rookie mistake is to do what's shown here, is just to break the large overbar into two smaller overbars and not to change the nature of the operator. And if you do that, well, then it's not correct. That's why this says is not equal to. Let's do an example of of using Boolean algebra here. So I want to go ahead and do basically the same theorem that we've already proven twice, but I want to show that you can prove it a third time. X or Y. Well, I'm going to AND each of those with 1. That's totally allowed. Anything ANDed with 1 is just that same thing again. So now I'm going to go ahead and leave the X and 1, but now remember that X or not X is also equal to 1. So I can substitute that in here. Then I'm going to do distribution. So y and x, we could also write it as x and y by the commutative theorem. Y and x bar, I'll go ahead and leave that one as y and x bar. But now you'll see that these first two terms here are x and something. X and 1 or x and y. So I'm going to say x and 1 or y. I'll carry through this last term here. 1 ORed with anything is just going to be equal to 1. And x ANDed with 1 is just going to be x. I'll use the commutative theorem to flip this one, and all of a sudden, we've proven that that theorem is true. So you now have enough information to solve two more example problems, the Boolean algebra example problem and the DeMorgan's theorem example problem. Once you're done with those, you're ready to come to class tomorrow.